Hello everyone. Let's begin with a simple observation. When you use a torch with batteries, the current flows in just one direction, from the positive to the negative terminal. This is what we call direct current or DC. But imagine the electricity that lights up your room. That supply doesn't stay fixed in one direction. Instead, it keeps changing direction, flowing first one way, then the opposite way, many times every second. That's alternating current, or AC. Mathematically, AC voltage is described by the function V of t equals V naught sine omega t. Here V naught is the maximum or peak value, and omega is the angular frequency. Have you ever noticed that the electricity powering your fan, fridge, or even the lights in your room isn't a one-way steady flow? Instead, it keeps reversing direction. That's because most of the electricity we use is alternating current or AC. Now, let's start with AC voltage. It is the potential difference that varies periodically with time, rising and falling in a repetitive pattern. And when this varying voltage drives the current, we get AC current. What's fascinating is that AC current follows the same sinusoidal time law as the voltage itself, meaning it also oscillates up and down in perfect rhythm. To describe this mathematically, both AC voltage and current can be expressed using sine or cosine functions. The equation looks like this: I of t equals I naught sine of omega t plus phi. Here, I naught is the peak current, omega is the angular frequency which tells us how fast the waveform oscillates, and phi is the phase angle, which shows how much the wave is shifted in time. As you can see in the diagram, the current waveform starts at 0, rises smoothly to a peak, drops back to 0, dips negative, and then returns again, completing one full cycle. The distance between two peaks is called the time period t, and the height of the peak is the amplitude. Along with frequency and phase, these three quantities, amplitude, frequency, and phase, completely describe any AC waveform. So, in short, alternating current is all about this beautifully repetitive pattern of rising and falling values. And this simple sinusoidal nature is the reason AC is so widely used for transmitting power over long distances, predictable, efficient, and incredibly reliable. Have you ever thought about why the electricity supplied to our homes and industries is almost always alternating current and not direct current? There are some very practical reasons behind this choice, and today we'll explore them. First, AC has a magical advantage. It can be easily transformed to higher or lower voltages using devices called transformers. This makes it incredibly flexible for different applications, from powering a delicate mobile charger to running a giant factory machine. Next, here's a crucial point about long-distance transmission. When we transmit electricity over hundreds of kilometers, we want to reduce energy loss. With AC, we can step up the voltage and reduce the current. High voltage and low current means much less power lost as heat in the transmission wires. This is exactly why power lines carry AC instead of DC. Now let's talk about the bigger picture, economy and efficiency. AC is more economical to generate, transmit, and distribute. Whether it's a power plant feeding a city grid or the line supplying your neighborhood, AC makes the whole process smoother and cheaper. On the other hand, DC transmission faces several challenges. To send DC over long distances, costly conversion equipment is needed to step up or step down voltages. This makes DC systems less flexible and less cost-effective compared to AC. So here's the quick insight: AC enables minimal loss in long-distance transmission, unlike DC. That's why from your ceiling fan to the national power grid, AC continues to be the preferred choice. Hello students! Have you ever thought about how deeply alternating current, or AC, is woven into our daily lives? From the moment you switch on the fan in the morning to the lights that brighten your room at night, AC is quietly at work everywhere. Let's start with the home. Your appliances like fans, refrigerators, televisions, and even computers, through adapters, all run on AC power. Without AC, daily life would feel incomplete, almost like a home without air to breathe. But it's not just homes. Think about industries, massive machinery, conveyor belts, welding equipment, and even the lighting systems in factories all rely heavily on AC power. Without AC, modern industrial production would come to a standstill. Now, move to another fascinating area, communication. Radios and broadcasting systems use the tuning principles of AC to carry signals. Imagine your favorite FM station, its AC at play, encoding and decoding signals to bring music right into your earphones. Medical devices too, from imaging machines to life support systems, depend on alternating current. Transformers and motors in these devices exploit AC's unique properties, making them efficient, compact, and powerful. And here's the quick insight: almost every electrical device around you, from a tiny mobile charger to giant city grids, is designed to operate on AC. As you can see in the diagram of the power supply chain, electricity is generated at about 11 kilovolts, stepped up to nearly 400 kilovolts for long-distance transmission, stepped down again to 11 kilovolts for distribution, and finally delivered to your home at 240 volts. All of this is made possible only because of the flexibility of AC. So, in short, AC is not just the electricity that lights your bulb, it's the backbone of modern civilization. Let's work through a practical example to understand the difference between peak value and RMS value of an alternating current signal. We are given a peak voltage V0 equal to 325 volts and the frequency f equal to 50 Hz. Our target is to find two things: the RMS voltage and the time period of the waveform. Now, recall the model equations. The RMS voltage is given by V RMS equals V0 divided by √2. And the time period is given by T equals 1 divided by frequency. These two formulas will guide us step by step. Let's substitute the values. Vrms equals 325 divided by √2. Solving this gives approximately 230 volts. For the time period, T equals 1 divided by 50, which is 0.02 seconds. If we convert that into milliseconds, it comes out to 20 milliseconds. So the result is clear: the RMS value is 230 volts and the time period of the alternating voltage is 20 milliseconds. Now here's the insight. While the peak voltage tells us the maximum push, it is the RMS value that represents the effective or useful value of AC. That's why in your home supply we say 230 volts, it's the RMS value, not the peak of 325 volts. This makes the concept of RMS voltage extremely important in real-life electrical systems. So, let's bring it all together. Direct current flows steadily in one direction, but alternating current oscillates sinusoidally with amplitude, frequency, and phase. Thanks to transformers, AC can be transmitted economically over long distances, powering everything from home appliances to giant industrial machines. And remember, the practical 230 volt supply we talk about is actually the RMS value of a wave that peaks at 325 volts. Alternating current is the very heartbeat of modern civilization. Without it, our homes, industries, and technologies would simply stop. I hope this session has given you a clear, powerful picture of what alternating current really is. See you in the next lesson, where we'll explore what happens when AC voltage is applied to a resistor. Until then, keep questioning, keep exploring, and stay curious.